Great. Okay, I see it now. So hi everybody. My name's Dr. Dominic Fritz. I'm an assistant professor here at Rensselaer Polytechnic Institute in the nuclear department. I do a lot of research in the at the Gartner-Linac facility, which you'll hear a bit about today. Joining us, we have 3 other faculty members and 4 students that you also hear from. Hunter, Seanbin. Do you guys want to go ahead and say a couple things about yourself, and then we'll turn it over to the students and hear from Tom.
Yeah, so I'm Dr. Hunter Belanger. I'm an assistant professor in the nuclear department, or in the main department, but nuclear engineering program here at RPI. And I focus on computational methods for nuclear reactor physics in nuclear reactor design.
Hello, everyone. My name is Seanbin Shi. My research focuses a little bit on the design of nuclear reactors, including advanced nuclear reactors. Happy to see everyone here.
Tom.
I'm the incompetent one on the group. I will be discussing my flaws and shortcomings. I'm also, this ties into what I just said in silent mode. I'm a professor of practice here, which means I'm practicing how to be a professor and apparently not doing well at it. That means I have a teaching career, not a research career. So you get all sorts of types here. And I'm also part-time the director of student services in Maine for the mechanical aerospace and nuclears. And I guess we should go around. Preston, I see you are unmuted, so let's jump right to you.
Hello, everyone. My name is Preston. I'm a senior nuclear engineering student. I'm graduating this coming May. I've been a nuclear engineer since I was a sophomore. I transferred from Aero because I enjoyed it so much.
Andrew, I see you right above. You want to kick in?
Yeah. Hi, my name is Andrew. I am technically a senior nuclear engineering student since my Arch semester finished. I have personally taken Professor Fritz's, Haley's, and She's classes. Yeah.
And actually, Andrew, you're joining us from Idaho National Lab on an internship right now.
Yeah,
right?
Actually, I'm technically in the office building at work right now. I found a little pod that will be quiet, so I shouldn't be interrupting too much. But yeah, I'm at an internship in Idaho National Lab. I've really enjoyed it. The nuclear engineering curriculum and the professors here really helped me secure this internship. She was one of my references, and Fritz has written me a letter of recommendation. So the professors here are really helpful and really nice.
Thank you. Grace, do you want to say a couple things?
Yeah, my name is Grace. I'm a junior nuclear engineering major. I originally came in undeclared engineering, but I declared my spring semester of my freshman year. So yeah, and I've had an internship. I've done all of that stuff. So I think we'll probably get into that later. But yeah.
Catherine, you want to wrap us up here?
Yeah, I'm also a junior nuclear engineering student, and I also came in as undeclared and declared nuclear in the spring of my freshman year. And this past summer, I got to intern at Constellation as a reactor engineering intern, and I'm returning there this coming summer.
So now that you've gotten to introduce everybody and see everybody and hear a couple things about us and who we are, we have a few slides prepared for everybody here that we're going to walk through. Just why nuclear and why nuclear at RPI and some of the facilities that we have here that are state of the art and one of a kind. Then we'll end off with some Q&A where we'll answer all the questions that you have and mostly try to have our students here answer some of the questions and then also hear from the faculty members as well. So with no further ado, I will get us started here. Can everybody see these? Hopefully in the big screen.
Yes.
Great, thanks.
Yes, looks good.
So, again, welcome to the Nuclear Engineering Program at RPI. This program has been around since 1961. As you can see, splitting atoms since 1961, where we actually had our linear accelerator first operational at the time. And just for some background, Rensselaer Polytechnic Institute, as many of you are aware, of course, is in upstate New York and specifically Troy, New York. And it was founded in 1824 and is the oldest technological university in the English-speaking world. So I'm sure you're wondering, why nuclear engineering, and then of course specifically, why nuclear engineering at Rensselaer Polytechnic. Well, there's many reasons why nuclear engineering is a great field and a great major. Whether you would want to go directly into industry or some other aspect of nuclear, there's many opportunities for you. Currently, the nuclear industry has seen a rather large resurgence driven largely by small modular and micro reactors. What are those? Well, if you look at the image there in the bottom left, excuse me, the bottom right, you typically are maybe aware of these large scale reactors that provide a lot of power to communities and perhaps cross state lines. These are very, very large reactors. They take up a large floor print and foot space, both for the core itself as well as for all the supporting systems. And these can be in range between 300 megawatts to 1,000 megawatts capacity. And a lot of the resurgence we're seeing today to help really drive, carbon-free electricity in this clean energy revolution is more focused on the small modular reactors and these micro reactors, which are much, as you can see by the image here, these a much smaller scale and therefore much smaller footprint, and they have a lower upfront cost to be installed. They can also operate in remote locations. For example, if you want to power a city in Alaska, for example, where it may be hard to transport fossil fuels, and something like solar and wind may not be available. And so why is this important, and why do people care about this? Well, industry needs operators, and industry needs reactor core designers, shielding designers, and many other aspects to actually get a nuclear power plant both designed, built, and operating in these various locations, ultimately to provide this clean energy future. And for some reference here, an average starting salary for an RPI Bachelor's of Science in Nuclear Engineering, this is a 2023 estimate, is around $80,000 or so. However, while many of you may be awfully familiar with a reactor, or may at least have heard of the term reactor before, there's actually a lot of other aspects to nuclear engineering. I actually had a little bit of experience in industry prior to coming back to RPI here, and this was actually in the medical radioisotope community. So what is this industry? Well, this industry focuses on, next generation nuclear medicine technology to both diagnose and also to treat various ailments, primarily cancer. If you look at the images here on the right, you can get some idea of the efficacy of this nuclear technology, where we look at various images and scans that were taken of cancer throughout a person's body, both before and after this actinium-225 treatment. And after just one treatment, and you can see there about 7 months of downtime, there's a dramatic remission in the cancer of this particular patient and individual, and that's such that they only needed one much more minor treatment, excuse me, and about 2 months later to go into full remission of this cancer. And so these treatments and these new technologies are cutting edge, and they allow us to quite literally save lives and diagnose problems sooner, to try to nip them in the bud so that they don't become a much larger tumor and much larger problem. And as you can tell, because this is so cutting edge and there's not a lot of experience here, there's a very high demand for experts in industry that can specifically both produce the isotopes and also ensure a very safe working environment due to all the radiation that may be present. The other aspect I'll mention here is environmental health and safety. So, in addition to all the man-made sources, whether it's a reactor or perhaps a cancer treatment facility, there's also a lot of naturally occurring sources of radiation. And I'll give you a prime example of one. There's one called radon-222. Every time you take a nice deep breath, you're inhaling radon. It's everywhere around you, and it's actually a large driving factor of your natural background radiation exposure. And because of this, we have to perform we have to perform environmental monitoring for these naturally occurring sources in addition to the man-made sources at all times, so that we can ensure that we know where they are, these sources are, the concentrations they are, and perhaps install mitigation plans if needed. As a result, there's a very, very high demand for what we call nuclear radiological engineers, or the other term you may hear is health physicists, both across industry and government research labs here at RPI, et cetera, et cetera. And I actually have a little fun fact here for you guys here. So did you know some food items, they actually are irradiated to extend the shelf life? And the reason for that is that you can have microbes and bacteria that may grow on, say a strawberry, for example, and you can hit it with a radiation beam to basically prolong the shelf life by removing all of those contaminants but still making it sure that it's perfectly safe to eat. And is actually, in some ways, it's safer to eat because you no longer have those biological contaminants. So in addition to industry experience and whatnot, there's also a variety of opportunities available both in various aspects of the government, primarily the military and the national labs, though there's also another big key body here, which is called the regulatory agencies. So in the military, whether you come to RPI and want to be a nuclear engineer, there's a couple different options. There's the Navy ROTC program. There's also the Navy NUPOC program. And they primarily interested in those to operate nuclear reactors and ultimately actually go and see the world. And of course, as you may be interested in, have you actually your full undergraduate degree paid for. However, they also have other opportunities too, particularly the Navy NUPOC. You can actually be asked to become a training instructor for those other individuals that would be interested in operating reactors. The national laboratories, where our good friend Andrew here is currently at and doing an internship. Many RPI graduates actually find their way there. With one caveat, typically the RPI graduates that are mostly interested in a national lab, they tend to get advanced degrees. They want a master's or a PhD degree to have, if they're more interested as a research scientist. However, there's still many opportunities for someone that wants to end just their undergraduate degree as well. It ultimately depends on if you want to go more into the operation space, the regulatory space, or the heavy R&D space, and it's all up to you. And then the last category here is, of course, regulatory agencies, which is essentially a regulating body. We have a prime example here, the Nuclear Regulatory Commission, or NRC, and they essentially create the rules and ensure that the federal laws and guidelines are being followed both by industry, academia, such as ourselves, and across the various national labs in the military. And here you see a nuclear-powered submarine, as well as also a nuclear reactor. And you may be interested to know that many of our submarines and aircraft carriers are actually nuclear-powered across the Navy. So the last major category we have here is, of course, academia. So in addition to just an undergraduate degree and getting a bachelor's of science in nuclear engineering, there's also opportunities available for you both here at RPI, should you choose to stay, as well as beyond RPI, as well as other academic institutions where you can conduct revolutionizing research. In the graphic and the image you see here, these are actually various RPI graduate students at the LINAC and also personal friends of mine. These individuals here, there's various positions available as a graduate student, what we call a postdoctoral researcher, which is essentially an individual that completed their PhD, but loved it so much at the LINAC, for example, that they want to choose and stay on as a postdoctoral researcher, continuing on with their graduate research. There's also research staff, full-time research staff, and faculty members such as myself. And so you may want to consider extending your learning through a master's or a PhD. And there's a very important note here. You may be interested to know that PhDs in nuclear engineering are, of course, paid. Quite literally, you get paid to go to school to get your advanced degree. So that's why nuclear, right? And why nuclear engineering? But why specifically nuclear engineering at Rensselaer? And why should you come here for your degree? Well, as you may have seen from some of our faculty members, we do have a wide breadth of research areas, and our faculty here are world-class in the research that they conduct. In addition, the facilities here are state-of-the-art and oftentimes one of a kind, as you'll hear about here in a couple slides. From a funding standpoint, for specifically undergraduate, there's various undergraduate scholarships and paid undergraduate research available, though the undergraduate research, you also have the option to take that for credit as well, as Grace is currently one of my URPs, for example. And she can tell you about that experience here in a minute. Also, as you can tell, there's opportunities in industry, in government, and in academia, and so ultimately you are free to pursue whatever your heart desires and where your nuclear dream may take you, whether that is in industry or government or otherwise. And then lastly, from our student standpoint, you'll benefit from engaging with other students who, like you, are among the best, and you'll work collaboratively, on multidisciplinary research projects. In addition to myself, Hunter, Sean, Ben, and Tom, there's actually quite a few other research faculty here at RPI. We have 6 full-time professors, Professor Malavia, Professor Danone, Professor Leon, Professor Liu, Professor G, and Professor Kang. There's 3 assistant professors, myself, Professor Shi, and Professor Bellinger. And then there's Tom and Clint, who are both professors of practice, as you heard about earlier. And then we also have a couple senior lecturers that help teach some of the classes here as well, Tara and James. Okay, so what do we actually do here at Rensselaer? You know, what are some of the areas where we excel and maybe a particular interest to you or others? The first category here, this is experimental radiation interactions and electron accelerators. The machine that you see there, that's actually the high power, high energy electron accelerator we have on campus. And we use this ultimately for nuclear data measurements to support fission and fusion reactors. We basically ask the question of, okay, well, we have this radiation that's present in this material and in this environment. What does it do? Where does it go? What kind of interactions does it cause? And we perform these measurements to ultimately understand that. We also leverage some of these measurements to generate both medical and also non-medical isotopes to solve critical supply chain shortages and to allow for the state-of-the-art research, such as the research in R&D into actinium-225, to progress further. And then lastly, a very large category here is we focus on the novel design of equipment for radiation environments. This equipment may be detectors to say, hey, there's a neutron here, hey, there's a photon here, it left at this angle and with this energy. We also may design equipment to survive in radiation in these harsh condition environments, ultimately to be, let's say, a water pump to provide cooling water to some of the targets that we work with. The next major category we have is reactor operation and characterization. And this is ultimately tying to the operation of a nuclear power plant to ultimately provide electrical power to a city or otherwise facility. And so there's many key aspects here. You have reactor risk and safety assessment. So, you know, what is the probability of an accident happening so that we can ensure that we have the appropriate safeguards installed and applied to make sure that that risk is as low as reasonably achievable. We also have modeling of the power plant operation and power generation system itself, as well as the heat transfer in the reactors, which is ultimately, you know, we have this core, we have this nuclear fuel, and we're generating this energy, but ultimately, how do we collect this energy and get it into a more useful form, which we typically use as electricity? The next 2 major categories we have is reactor physics and nuclear materials. So building on the previous category, reactor physics is all about, you know, understanding the physics inside, you know, the bread and butter of the reactor, which we call the core. In this case, we have, you know, various particles and radiation particles traveling around. The most important one is what we refer to as the neutron, as this one will drive our largely fission-based reactions. And so our faculty here, they perform computational and experimental reactor physics and radiation transport theory and computational-based calculations. In addition, we'll also assess radiation effects on specifically electronics, though other materials are of interest as well. And then the last major category here is nuclear materials. So this is kind of branched into two main categories. We want to understand, in some cases, the ultimate and fundamental behavior of the material itself from a molecular dynamic standpoint, and then also use this information to design ultimately new and novel materials, primarily to be accident tolerant, right? So in the event that the reactor gets really, really hot, as an example, we want to ensure that there's essentially a 0% chance that this fuel should fail or melt. In addition, we also concern ourselves with advanced nuclear waste management, right? So we operated our reactor, but what do we do with all of this spent fuel? Is there a way that we can design a reactor to produce less radioactive fuel or just less fuel, less radioactive waste or less waste altogether? And so in order to support the various research that you see here, there's a variety of research facilities that we have. The largest one is actually the Gartner-Lennox Center, and that's where I myself work. And this heart of this center is a 60 MeV electron linear accelerator, which we use for a variety of applications. And if you look down at the image there in the bottom right, you can actually see just how large the facility is, where this is a Google Maps image, and you can actually see the football field of the RPI campus, which is actually smaller than the entire LENAC facility if you account for the flight stations, and especially the office spaces. So what do we use this for? Well, we conduct nuclear data measurements primarily. We wanted to conduct these measurements, as I mentioned previously, to understand ultimately, you know, how these radiation particles are interacting with various systems ultimately to improve both fission and fusion reactors. If you can't understand how these particles are interacting in these systems, then you can't design a reactor. In addition, we're also very interested in medical radioisotope production, ultimately to diagnose and treat cancer, as you saw with the actinium-225. And then lastly, we also are very concerned and interested in radiation damage, as you know, ultimately we need to understand whether it's a mechanical component, electronic component, just a base material, how well it's going to survive a high radiation environment, as it may be a candidate material for use in a reactor or perhaps a space application where, of course, there's radiation present. And you may be interested to know that this is actually the only facility of its kind in the US. So if you're interested in this kind of research and to get involved in this kind of domain space, I strongly encourage you to come work at the Gardner-Lennox Center, where you'll design, build, and ultimately discover new physics. However, the 16 MeV electron accelerator at the heart of the Gardner-Lennox Center is not the only radiation lab that we have. Also located at the facility, we have a neutron laboratory where we have calibrated californium-252 sources. What are those? These are radioisotopes. A specific radioisotope that spontaneously fissions. And when it spontaneously fissions, it produces a spontaneous source of neutrons that we can use to probe detectors and ultimately study radiation interactions. We also leverage the use of a DT fusion source located here for also fundamental neutron research, in this case with higher energy neutrons that are more of interest to fusion applications. Located here is also a nuclear engineering laboratory, which if you choose to come and perform your undergraduate degree here, this will be a critical foundation to your degree, where you'll take several classes here that engage with hands-on experimental research. And then lastly, we have our radiological engineering lab, where you also get some hands-on experience working with some of the detectors and some of the facilities here. But we also leverage this laboratory for various radiation detection and ultimately as a health physics lab to make sure that everyone is safe here. In addition to the Gardner-Lennox Center, we also have our Nanonuclear Center, which is ultimately to study materials. As I mentioned previously, we're interested in these accident-tolerant fuels, these effective nuclear waste management, and radiation damage and radiation effects, where you can see some of these in the slide the image located on the slide to the right, where we may be interested, for example, in microscopic holes that form in the material that may cause a defect and ultimately a failure of an electronic component. In addition, we also have a thermal hydraulics laboratory that focuses on two-phase fluid flow and power transient reactors, where the two graphics you see here, one of them is a heat pipe test facility and the other one is a two-phase flow facility. For those of you that may be wondering, two-phase flow is essentially if I have water boiling, for example, I'll produce some level of steam. But if that water is traveling with that steam, now I have two phases, a liquid and a gas phase, flowing through my pipe, which changes ultimately the characteristics inside of that pipe. And the last major research facility that I'll mention here, but this is of course not the extent of all the research facilities, is our actually new reactor simulator that we're currently installing, and will actually be having our grand opening on this coming Monday. So you should strongly consider coming for an accepted students day. This newly installed reactor simulator, what does it do? Well, it actually does what the name implies. It simulates real-world nuclear power plant operations, specifically focusing on reactor transients and accident situations and scenarios, so that before you'd go into industry or before you'd go operate a nuclear reactor elsewhere, you can get some hands-on experience and see just how these scenarios actually unfold in a reactor, both from a physics standpoint and from an operator standpoint. So what is the student experience? Well, if we had to pick two words, we typically describe it as engaging and dynamic. We have a very broad spectrum curriculum, and as you may be able to tell, it's a very project and applications focused courses. There's a lot of hands-on experimental courses that will require you to work with radiation sources and detectors, and of course, very safe radiation sources and detectors and other mechanical devices. There's also a year-long senior design team project where you and several other nuclear engineering students will design and develop a project of your choosing. And then lastly, I'll mention here is we also have independent study undergraduate research. So you're allocated free electives in the nuclear engineering program, and you can take courses, or you can speak with a professor such as myself, Professor Bellinger, and other professors here to engage in an undergraduate research, ultimately of your choosing as well. And what you see here is you can see some of the hands-on research experience of some of the students here, as well as some of the undergraduate student presentations that you may be asked to complete. So, our students, how many students do we have? What is the size of our program? How many nuclear students might you expect to interact with? For the Bachelor's of Science, we have 74 declared majors. And for PhD students, we have 22, and then we have 5 master's students. And for some perspective, in 2023, we had 16 Bachelor's of Science graduate, 4 Masters of Science, and 5 PhD students. There's many fellowships and support, funding support that you can get both as undergraduate and as a graduate student, if you so choose. So if you're interested in research, please by all means reach out to any of the faculty here as you so choose. This is my last slide here, where of course we ask you to come advance nuclear at RPI, and I ask that you make sure you join us during Accepted Students Day if you're interested on March 22nd or April 12th. And if you choose to come one of these days, please let us know ahead of time so we can appropriately schedule a tour of the various research facilities so that you can get a nice view in person. The link that you see here, this is the link to our webpage if you want to read more about some of these facilities. And with that, I'll end here and we can open up to Q&A.
And I'm not sure if anybody can chime in audio, so please throw some Q&A into the chat. And I just want to mention one thing. Dominic, Professor Fritz mentioned that there were 16 graduates last year, and there's 74 total. And you might be thinking, wait a minute, is there like an attrition rate? Do people fail out? That kind of thing? Our numbers have actually been increasing. So there's more juniors on the way in the pipeline, even more sophomores in the pipeline, and hopefully you will be even more in the first year. So with that, please drop your questions in the chat or however you choose to communicate them to us.
We don't seem to have any questions in chat, but that is really the only way that they can communicate with us.
We have one here. Is it possible to double major? And Tom, you may be the best one to answer that.
Yeah, we were just discussing these, as a matter of fact. So there are two kinds of these amalgam multidisciplinary majors. There are double majors and dual majors. So I just want to indicate that your vocabulary may not quite be your intent. A double major is where you get 2 diplomas. And on average, it typically requires the student an additional year, unless you bring in a lot of AP and IB and whatever credit, or you take a much higher course load. And you simply satisfy the requirements of 2 different majors where you get 30 more credits. A dual major sort of synthesizes 2 degrees. And this is a dangerous thing. How could that possibly be? A number of our dual majors are dual majors because, forgive me, parents listening in, your parent comes to you and says, or a guardian or whoever, and says, you know, this is expensive, get 2 degrees for the price of 1. And no company wants to hear you say that. What they want you to say is, wow, nuclear engineering is really cool, but it obeys the laws of physics, and therefore it doesn't go wrong. It does what it does. The part that goes wrong is the mechanical engineer's fault. It's the stuff that breaks. So maybe I should dual major in mechanical. You say that to a company, they're going to hire you. They're going to say, well, hopefully, they're going to say, you understand why you did a little of this and a little of that. That's really good. And if you look at the employment of the Nuclear Regulatory Commission, most of them are mechanical engineers. Why? It's the stuff that breaks. But the nuclears are absolutely vital to the design and the operation of the reactor. So yes, we have dual majors, we have double majors. The dual is the most common. In mechanical, we have a few aero duals. Some of them, half of them, are because they want to be boots on Mars, and they know the only way we're going to get there is with nuclear reactors on the ship. That is a long answer to a quick question.
Thanks, Tom. I see the next question here is working one of the jobs described doing only calculation, or is there hands-on stuff? And the shorter answer to that is it's entirely what you choose. There's many jobs that are actually only hands-on. There's many jobs that are only calculations. You can sit at your computer, you can work remotely if you so choose. Some positions are actually fully remote. I know there's a company, Westinghouse, loves to hire remote positions, and actually my experience and when I worked at industry is that it was very much a hybrid. I could, if I had experiments and hands-on stuff I needed to do, then I would be in the lab every day. Now, if there was calculations I needed to do, I could stay at home and I could work remotely and of course have WebEx calls and Teams calls with those I needed to have. But if there's not a need for me to go into the work environment, then I did not need to do so. And I know Andrew's here actually as well, and he's currently at a national lab. And you see him in the office. And Andrew, I don't know if you want to say a couple words on that too.
Yeah, so I am doing a job that could probably be fully worked remotely, but INL's current policy is that we should be moving back to in-person work. So I am fully in person. However, if you do, there are exemptions and you can get a laptop that's on INL's network and you can do all your calculations, you can do all your meetings from home. It is currently hybrid, but they are moving back to fully in person.
Thanks, Andrew. And what I've seen the most common is there'll be a handful of individuals that will do focus on calculations, and there'll be individuals that focus primarily on the hands-on aspect. And so what you choose to specialize in is entirely your choice. I don't know if anyone else wants to add anything on that.
I was just going to say exactly what you said, Professor Fritz, is that as an example, I do pure computational work. That was my entire experience before coming to RPI and my PhD, and then my brief time in industry as well. And now here, I develop simulation tools that work on advanced supercomputers. So it's still really cool, or at least I think it's really cool, making software, specialized software that runs on the most powerful supercomputers that we have on the planet is really challenging. But it means I'm not playing with radiation sources or detectors very much myself. But that's okay. I am still very happy. It's about finding what you like.
Professor Belanger has me to go play with the radiation sources on his behalf. Thanks, Professor Belanger. The next question I see here is there an opportunity to study abroad? The answer to that is absolutely. And actually, one of our students here, Grace, she actually, if I recall correctly, did an internship abroad in Dresden, Germany. And Grace, I don't know if you want to say a couple words about that.
Yeah, so when I was coming into college, I really wanted to study abroad. That was kind of one of my top things that I wanted to complete. And definitely with a smaller program, I would recommend start as soon as you can to try to plan it out. The study abroad office is small, but they're very helpful in planning out your schedule. I think where it came down to it, like my freshman year, I was kind of interested in it, but I didn't really take any steps to plan out how my schedule would look. And it's definitely harder with a smaller program because most of the classes are only offered at a very specific time. Like right now, I'm in the spring of my junior year and we don't have any major specific classes offered for our year right now because this is kind of where it falls in with Arch and stuff like that. So definitely planning is key. Most of the stuff that goes into study abroad is making sure that everything can get approved and you'll be able to get credit through RPI. But the program that I ended up doing through the study abroad office ended up being an internship, and it's the only one like it. A lot of them are just you're studying, taking classes, but mine, I was working in a lab that was through the Technical University of Dresden. So I'd say it was a very comparatively complex experience to working at the LINAC and stuff like that. So I think I got a very good experience, but it's definitely all about planning, but it is tough.
Thanks. Excellent. Next question I see here, are there any summer classes or opportunities at RPI for nuclear engineering? Again, the answer to that is absolutely. There's a lot of research opportunities here, both you can take for course credit during your normal academic year. You can also stay over a summer semester and get paid to do research here if you work with a faculty member. For example, if you want to do hands-on work at the LINAC, if you want to do computational work with Professor Belanger, if you want to do thermal hydraulic work with Professor Shi, all of us are, of course, always looking for students, and particularly good students, to come work with us. So there's absolutely opportunities both during the academic year and during the summer semester to do research here, and of course take classes as well.
Yeah. I think I might just caveat that though
yeah.
with, I don't think there are nuclear specific classes over the summer, though, is the one thing. And Tom can
Yeah.
correct me if I'm wrong. So you'll have many opportunities if you want to take classes for credit over the summer that fulfill requirements in your degree, but they won't necessarily be nuclear specific. So like you won't take physics of reactors over the summer or radiological engineering. Nuclear specific classes aren't offered in the summer, unfortunately.
Thanks. The next question I see here, there are many different types of jobs in the nuclear sector. Many
No,
are
that was
hands-on.
that was my response to one of the
Oh.
questions in the chat.
So, I see it. Thanks. Appreciate it. Dun. How many
Catherine
and what
or
kind of
Preston. Sorry, Catherine or Preston, do you ever go to
Oh.
the American Nuclear Society meetings? Do you have anything to add?
I'll admit that I'm more of the social introvert type, so I attend only a handful of those meetings. But I am in their Discord server, and I do definitely check them out. They have a lot of cool activities. I know that upcoming they have a tour of I forget which reactor, but they're going to a operating power reactor and taking a tour of that coming up this time sometime in April for students.
Good night.
They do a lot of outreach like that, so it's basically a great way to connect with fellow nuclear engineers and go out and do cool activities. I know I mentioned the tour, but this is not just a one-time thing. Like they're always scheduling things like this. They bring in guest speakers to speak on the different research topics. So it's a really great way to see a lot of different perspectives on nuclear engineering.
And actually, Catherine, if you want to maybe speak to some of the other clubs on campus, I know you're involved in a couple of them.
Yeah, so I'm in like a bunch of the Discord. I also don't regularly attend the meetings, but there are a lot of professional outreach programs, which is great to get some internship opportunities. And yeah, they are planning a trip to the Gannett plant, I think next week. So that's pretty exciting. And I think it's just a great way to like talk to other nuclear engineering students and make sure that everybody can help each other out.
Thanks.
I will piggyback off that, just talking about other clubs at RPI. While there are very few actual nuclear specific engineering focused clubs, there are a bunch of different engineering focused clubs on campus, and they're more than willing to have nuclear engineers work on their teams. While I'm not really active in ANS, I am a part of Design Build Fly, which is an aeronautical based club. Essentially, what they're doing is they do a lot of aero work. They design a little aircraft to fly at an international competition. Even though I'm a nuclear engineer, there's still plenty of roles for engineers on that team, whether it's doing finite element method analysis, which is something you'll also see somewhat a bit in nuclear engineering, or just working, just generally speaking, on checking out things, making sure that the design proposals look good, or all sorts of work. And they're always willing to have all sorts of different majors come and do that. So if you're concerned about having like not enough activities, there's always engineering activities that you can be doing, whether with nuclear or with one of the other clubs on campus. It really doesn't matter.
There's of course also a lot of non-engineering based clubs as well. There's I don't know if any of you are involved in the humans versus zombies club, and there's various other sporting clubs and whatnot, activities, intramural sports and whatnot. So in addition to the engineering clubs, there's of course the non-engineering ones too. The next question I see here is if I'm also interested in materials engineering, would a dual major between those two fields be a viable choice from both a student workload and a professional standpoint? You may not actually need a dual degree there. Now, you could pursue one if you're interested, but one of our professors here, Professor Leon, he's very focused on specifically nuclear materials. And what I might encourage and suggest you do is you could get a nuclear engineering degree and work and do research with Professor Leon and learn all about the materials aspect to try to bridge those two fields without having to take an exact dual degree for that purpose, unless you just wanted to, of course. And then, of course, there's also advanced degrees that you can consider too, if you are still interested in the nuclear domain space, such as developing new accident-tolerant fuels.
I want to mention one thing on top of that RPI, in contrast to many other schools, has a remarkable number of free electives. Now, if any of you have siblings in the School of Science at some other university, you'll say, you've got nothing. We only have 12, so you can take 3 or 4 courses. But among schools of engineering, it's remarkably high. So you don't have to dual major or double major. You can still say to a potential employer, hey, I took structure of engineering materials from the materials science department or materials engineering department, and I took kinetics of materials and dovetailed that with my nuclear materials coursework, and they'll buy it. They don't need to see that you had a dual degree, because again, there are a few companies that say, why did you dilute in 2 directions? But your perception is spot on. A lot of the challenges in the nuclear world revolve around finding the right materials. So your intuition is right. It might actually, as Professor Fritz says, it might actually be a lot easier to pursue that passion without having to go the dual major. Also, this is an aside, materials engineering doesn't really play well with others. If you want a dual major with materials, their attitude is, yeah, get the materials degree and then we don't care what else you do. So they basically want you to do, there's no concessions to make it easier. There you go.
That was a perfect addition, Tom. Thanks. The next question I see here is how math heavy can nuclear engineering jobs be, and how much math does one learn in order to earn their nuclear engineering degree? I think that one might actually be best answered by maybe some of our students here. I don't know if anyone wants to hop in, take a first stab.
I can say, so I in high school took like up through Calc BC, and then in college I retook Calc 1, retook Calc 2, and then I took multivariable calculus and differential equations, and that was kind of it for like fully math, but like every course that you're taking from then on that's nuclear like is math heavy, and that's just kind of it. It's a lot of integrals, I'd say, and like finding different equations and like understanding how they work. So I'd say that nuclear in general is very math and very physics heavy.
Yeah, great. Does anyone, Andrew, do you want to build on that? Yeah, go ahead.
Yeah, so it can be completely math heavy, but at my internship at INL, I have done almost no math at all. It has been, I know that sounds bad, but I have been mainly working on writing code and doing probabilistic risk analysis, which sounds super math heavy, but it's mainly just analyzing the results you get, making sure they look right, and making sure that your code is operating how it's supposed to, doing code patches and stuff like that. So it doesn't necessarily have to be code heavy. Math heavy, but it definitely can. I've seen some of the work that thermal hydraulics guys have done, and that is certainly math heavy and physics heavy. Professor Shi, I've seen one of your grad students here at at INL, and he does a lot of math heavy work and a lot of simulations and stuff like that. But me personally, it doesn't necessarily have to be math intensive. It's always good to learn though.
I can add a comment on that too. You can learn the math and then you can write a computer code so that you don't have to do the math anymore. You have the computer code do the math for you, of course. You still need to know the math. You need to make sure the code's correct at some point, of course. And we call it validation and verification. But to one degree or another, it's up to you to what degree you want to go into math. If you want to go and do research into reactor modeling and physics calculations, like Professor Belanger here specializes in, I think he does math all day, every day, to his heart's desire. But from the experimental side, you may do some math to design an experiment, but then ultimately you have to go and characterize the experiment, and there's a lot of non-math intuition that you have to build on and experiment with. And so to what degree you want it to be math focused is largely within your control. I'm interested in the next question I see here is I'm interested in nuclear fusion. Are there classes that focus on it? There is a class that has been taught for nuclear fusion that we are looking to offer again in the near future. In addition, there are nuclear fusion sources here on campus, specifically at the LINAC, that we have one, and we're actually looking to acquire a second one to ultimately understand how specifically fusion neutrons behave and interact in nuclear systems. Tom, I don't know if you want to add a little bit more onto the course aspect there.
I'm actually the voice of doom and gloom on this. In 1983, I took the nuclear fusion course, and prior to that, I thought, I think I really want to do that. And I took this course, and I came up with a conclusion that fusion would be here in the way that I wanted to do it, either after I was retired or after I was dead. And my conclusion is still coming true. So I'm sort of down on the whole thing. However, we need really good, really smart people working in this area because it is achievable. I genuinely believe that. It's a question of when. So here's a choice for those of you who are passionate about fusion. On the one hand, you would like to be in an undergraduate community where lots of people around you are also really passionate about fusion, and you will not find that at RPI. You will find interest, you will find a lot of discussion, a lot of good work, and a lot of research from different angles, but there's not that core, maybe next year we're going to do it, or maybe the year after. That group is not here. Now, the catch is we don't need undergraduates in fusion yet, anywhere in the industry. Occasionally they do get jobs, but pretty much the industry, with a few exceptions, doesn't need undergraduates. So why would you come to RPI? Solid foundation. Being a nuclear engineering major, you would have the background to go to a graduate program, which are the people they really need, the people really pushing the frontiers of science to get the job done. So again, you would come here to be in the milieu of undergraduates, and like me, maybe you get, brought to the fission side and you say, oh, there's a career there. But again, yeah, you're more than welcome here, and there are people talking about it. But there are other big schools that are like fusion any day now, and if that's the environment you want to be in, also definitely be looking at them.
I can actually add a comment on that too. One of the big challenges with fusion isn't as much how do we make fusion happen. We've known how to make fusion happen for quite some time now. I mean, we have a portable fusion device, here at the LINAC, and I can go make a fusion source of neutrons here once we're done with this meeting, if I so choose. The problem is, how do you make it economical? And how do you make make it competitive with fission reactors or natural gas plants or hydropower or solar power? And so some of the research that we are interested in doing here, and some of the other universities are also getting interested in, is less how do we get fusion to work, but what are some ways that we can make it more economical? And I'll give you an example, right? I mentioned the medical isotope production. There's a million ways to make medical isotopes. And one of the ways that there's a lot of interest in is, can we use fusion reactors to make medical isotopes? Because there's a rather large need. And actually, one of the students here, Preston, is working on an end-to-end senior design project to try to see if we can make that actinium-225, the world's rarest drug, using a fusion reactor. Why would we want to use a fusion reactor? Well, ultimately, a fusion reactor produces a lot of fast neutrons that are actually mostly treated as a problem. They go and they throw a bunch of shielding material and they say, wow, we need to stop these neutrons. And that costs money when you have to have all the shielding material and you're not really actually using it for anything. So if you can figure out novel uses for it, such as making isotopes or otherwise, and then now you start changing that economics equation. And Preston, I don't know if you want to touch on a couple things about your senior design project.
Oh, certainly. I think this was on a previous slide that Professor Fritz shared, was essentially your year-long senior design project. For us, my group, we went along with medical radioisotope production. In this, we're particularly looking at the actinium-225 production, as you mentioned. In this, we have an obvious importance of using something like neutrons for that. But one of the best parts about the entire project is that it's largely student-led. Like, we came to the understanding that we need to use neutrons to produce actinium-225, not because we were told we have to use neutrons, but because we tried out, like, how does photons work? How do protons work? How do deuterons work? And then we come to the understanding, well, of all those methods, really neutrons are the best. And now we're working on trying to develop a way to say, like, how do we actually do this? And I actually had a meeting earlier today to just go over some of the simulation stuff that we're working on. And so it's a really great way to kind of work on these sort of real world problems, which I enjoy and I know my team enjoys as well.
Yeah, thanks. The next question I see here, these are more, maybe more for you, Tom. Is it common and or achievable to earn a dual degree, including nuclear engineering, along with a minor in something else?
The very quick answer is no, too much. A dual major, yes. Dual major and a minor. Oh, sure, yes, you can do it in 5 years, but not in the traditional 4. And if you were to go that direction, what we would recommend is work really hard and qualify for a graduate degree. And rather than spend 5 years and get 2 undergraduate degrees and a minor, get 1 undergraduate degree and then do your master's in a second field, or and add spice along the way with elective courses.
Thanks. I had also another question for you here. How transferable are credits such as AP, IB, and dual enrollment?
I don't know, Randy, do you want me to let admissions give the official word on that?
Absolutely. So we accept up to 32 transferable credits. For APs, we're looking for a score of a 4 or a 5. IBs, a score of a 6 or a 7, and then college level credit of a C or better, as long as it's above and beyond the high school requirement. So 32 transferable, and that would all depend on what they're in, and would they relate to your actual courses, or would they be electives? That'll be reviewed by the hub within engineering.
Perfect. Thanks. How should I shape my education if I'm interested in advocating for nuclear energy and defending it politically for the purpose of helping the industry and the future?
Give a brief comment below saying we have a really
Okay.
strong STS department, and Haas credits go towards that. We don't have nuclear specific classes, but it certainly comes up in many of our nuclear classes, the social science issues behind it. We have some really good debates in some of these classes.
Yeah, and I think actually to build on that too, in our senior design projects, as you go about and you conduct your senior design project, in addition to designing something from the engineering aspect and how it might work, you also have to take into account social and economic aspects as well. Is it affordable? Is it cost effective? Is it saving lives? Is it maybe not saving lives? Things of that nature as you weigh designs in person. You can add a couple comments on that too.
Yeah, I would say that the professor or lecturer who runs senior design, his name is Professor Olson. He himself is actually very emphatic on the importance of bringing in the wider community into nuclear discussions. He's not an actual like full-on researcher here at RPI, but he does a lot of work in just keeping like in community engagement and involvement. He has a couple of DOE grants working on that. And that's one thing we were continually stressed throughout the design, throughout the senior design process is just the importance of considering the community. We have people from different departments, like the environmental department, come in and just like sit in on some of our presentations and our meetings, just to make sure that we're all like taking into account some of these different considerations. And that also helps us learn how to kind of tailor what we're saying to a wider audience instead of just focusing on what nuclear engineers understand, which is really important for that community outreach.
All right, thanks. The next question I see here is how close-knit is the student environment as a nuclear engineering student? Maybe I don't know if another one of the student wants to take that one. Yeah, go ahead, Andrew.
Well, I think Fritz and Professor Shi have seen that I always sit right next to 2 of my good friends, Owner Taishi and Aaron Sukov. And in almost all of my nuclear classes, we hang out outside of work or outside of school. We work on projects together when we can. We work on homeworks together when it's allowed. I think I see the nuclear engineering students pretty much every day because our classes are really small. So it's really easy to talk to other nuclear engineering students and foster a sense of community between us, since there's only like 20 or so students in each class, which also really helps with professor interactions as well.
Great, thanks. Grace, Catherine, do you guys want to add anything to that?
Yeah, like what Andrew was saying, it's a pretty small major. So at least like for the women in nuclear, there's I think like 7 or 8 of us in our year, and we all have a group chat. We all do homework and study together, which I think is great, just helping each other out.
Yeah, great.
I'll emphasize the line that I hear a lot from students, regardless of their major, that's one of the reasons why RPI is attractive. We are a remarkably good school for our relatively small size. So with this many students, you get to interact with all sorts of different majors, different people, but you get to know a lot of them, a remarkable number of people. And especially, as Catherine was saying, within nuclear, you get these smaller groups. RPI in general is, and please students, tell me if I'm not right, we try to be very collaborative. We encourage students to work together. It's not just like, oh, did Catherine just say she works with other people on her homework? No, she's supposed to. You're going to learn so much more. So yeah, that collaborative spirit we find is really good here. And in nuclear, it tends to be tight, but don't let me sell you on that. Let the students say more.
Yeah, I was gonna say that too because I saw another question about what made RPI my top pick. So I was like doing my college search during COVID, so it was super hard and like no schools had tours or anything, but I toured a few, and while walking around campus, it was kind of like I just felt like the feeling that everyone was feeling, and everyone was stressed and everyone was sad, and I just like I obviously like everyone that goes to RPI was an overachiever in high school, and that's just kind of how it is. So I think we all kind of get it in that it's like, yeah, school is important, but it's also important to like take care of yourself. And I think that's definitely something that's very talked about at RPI. And even from when I like stepped foot on the campus, it just like felt that people wanted to be there. If that makes sense in the strangest way. But I think definitely the feeling of collaboration, because in the end, you're going to be working a job and you're going to be on a team of people and you're working with other engineers. So you have to learn how to work with other people. And it's not about a competition. Like, we're all trying to work together to accomplish a goal. It's not one singular person is going to be like the smartest person in the class and it's going to do all this stuff. No, like we're all like collectively trying to intake this information and accomplish something together.
Great, thanks. Thanks. There's another question I see here. In your experiences, is there a specific graduate degree that you think is essential / helpful in the nuclear energy field? I'm not sure if this means graduate degree from like a BS, master's, or PhD level, or graduate degree from like nuclear, mechanical, aeronautical things of that nature. So I can touch on both aspects. Um, from from the major specific, both nuclear and mechanical are in very high demand in the nuclear space. In the nuclear industry and nuclear domain space. We need nuclear engineers to design the cores. A mechanical engineer cannot do that. They can say, oh, well, from a stress standpoint and from a structural load standpoint, I can design, the fuel cladding to be, such and such thick, and I can design the heat transfer to come out of the fuel, but the mechanical engineer is not going to know how to arrange the fuel and how to design the control rods and how to design the safety systems to make sure that you have a safe, of course, regulatory compliant core. Now, having said that, while a nuclear engineer does that, ultimately a mechanical engineer is going to be more specialized in helping to take the heat out and ultimately generate power from it. Now, of course, that's the reactor example, and there's many other examples. If we go to medical isotopes industry, I can say I worked with many mechanical systems engineers. I actually worked with on any given day. I think I spoke with 10 mechanical systems engineers and maybe one nuclear engineer. As the nuclear engineers were expected to be experts in their domain space because there's not a whole lot of us, and there's a lot more mechanical and mechanical systems engineers. And so if you're trying to specialize in one or the other, it may be beneficial to specialize in the nuclear space and then switch and learn some of the mechanical aspects rather than specialize in the mechanical space and try to pick up the nuclear aspects later on if you do want to apply in the nuclear space, specifically nuclear energy space, which is what I see here. Now, from a degree standpoint, it ultimately depends on what you want to do. If you want to be an operator, and you want to follow procedures and have operate a reactor that's already been operated before, for example, a bachelor's of science is more than sufficient to achieve that. Now, if you want to go and design certain systems that would go inside of the reactor, but maybe not design the reactor overall, you may want to consider a master's of science, or you may need some experience in industry or in government or elsewhere before you'd actually get involved in the designing of those components, at least seriously. Now, if you wanted to say, oh, I want to design the entire reactor core, or I want to be heavily involved in the design of an entire reactor core and understand exactly how it's put together, you may want to consider an advanced degree like a PhD, because what separates a PhD from a master's degree, fundamentally, is a PhD is an individual that makes a contribution in terms of research to the field, where a master's degree will learn about basically what has been done in the field and then apply that knowledge.
We're right at the 7 o'clock hour, so maybe we can
Okay.
adjust the one last question in here. That would be to the students, and what made you decide to come to RPI to study nuclear engineering? We can end it with that.
Thanks.
I could touch on that. So I was deciding as an incoming freshman between RPI and Carnegie Mellon as an undeclared engineering major. So I ultimately picked RPI because of what Chris was talking about, like the environment of being surrounded by STEM majors. I think it's very different from like a larger university where you have liberal arts students and just being able to like have friends in all of your classes and everybody's going through the same thing. They're going through the same struggles of taking all the math and science classes. So I think really just the environment of RPI, as well as all of the specific majors, like Carnegie Mellon did not offer nuclear engineering. So I thought that was awesome that RPI has more specific engineering majors.
I can go next. I think Grace partially addressed it in how she felt that everyone there was kind of going for the same thing. Everyone felt like a little bit, at least as of a high school overachiever, coupled with the fact that nuclear engineering isn't offered at a lot of schools. It offered a very unique and interesting experience for you to go into. I started as a nuclear engineering major and not undeclared because I always really was interested in nuclear engineering from the beginning. I thought RPI was one of the best places, partially due to LINAC, which, like Fritz said earlier, is one of the only stations like that in the US. And I just really, I really just wanted to go to RPI from the start.
You want to give a comment?
I'd say that I'm probably not as qualified to talk on this topic because of me coming in as an aeronautical engineer. But one thing that made me choose RPI for an engineering program in general over any other of the schools is one, I saw its small size and really attracted to that. I'm originally from Texas, so we came from a very large high school, but I had some experiences in middle school of smaller class size and realized how important that was and just helping me enjoy what I do and what I learn. So that was one of the largest attracting features of RPI to me. Its aero program is also pretty good too.
And does anybody want to add in the chat how anybody could reach out if they have any further questions about nuclear engineering? They can reach you by email.
Yeah, absolutely. I mean, so of course, all of our emails, if you go research, look up any of our names, Professor Fritz, Professor Belanger, Professor Haley, Professor Shi, you'll find all of our emails online. If you just look up RPI, we can also post them in the chat here too, for those of you as well.
All right, I think we should wrap up, but we want to thank everyone for being on tonight's session, asking all your great questions about nuclear engineering. Thank you to all of our panelists. And again, this session is being recorded. So if you'd like a copy, you can always email us at admissions@rpi.edu to obtain a copy.
Thanks everybody for joining.
Yeah, thank you so much.
Thank you.
Students especially.